Hello everyone, today we are going to discuss topological sort. What this algorithm do is it helps us to sort a graph. When we are saying to sort a graph, what we mean by this is, let's suppose we have two nodes u and u is pointing to v. So if you want to reach till v, you have to come through u. This is the process, this is the way. If you want to reach to v, you first visit u. That means you will always come before v. That's what sorting is all about. So if there is any two nodes that are connected in such a way that a particular node is coming before the significant other nodes, then the sequence will go accordingly. This sorting is very helpful for your questions like course scheduler, to find out the safe nodes. Any question or any approach which requires you to manipulate the graph or read the graph in a sequence, or to in such a way that the starting position matters more than the end position, or where you have to go step by step, all those places you can think of a topological sort. I'll draw a diagram to depict more on this. So what I'm saying is, let's suppose there is a node u, v, w and x. So these are the nodes, and we know that if we want to reach v, we must go through u. If we want to visit w, we should visit through v. If we want to visit x, we should visit through v. So if someone asks that what is the sequence you can expect, we can expect this. U will come first, then v, and then any of these value can come, w or x. Any of them can come along the side. So that's what comes to our mind when we say sort or topological sort or sorting of a graph. Now let's discuss how can we find out the topological sort at the end of the day. So what we are going to use, we are going to use a BFS approach. And when we ask for a BFS approach for a topological sort, it comes out to be Khan's algorithm. So let me tell you what is this algorithm is all about. So there is a concept which you can use which involve in degree. So if you see carefully, if we take this example, correct, we can see what is the in degree of each node. This node have 0 in degree. When we are saying 0 in degree, that means there are 0 nodes that are coming towards 1. If we talk about 3, the same thing is there. There is 0 in degree. If we talk about 2, that means it have 0 in degree. There is no incoming edge to this. What does this 0 represent? That means that this 1, 2 and 3 are not dependent on any other node. They do not want any other node to be visited first before visiting these nodes. These are individual nodes. We can start off with these nodes and can reach to our destination. So that's what in degree 0 means. If we talk about 0, so it's in degrees 3. What does this mean? That there are 3 places, or there are 3 nodes which are coming towards 0. Okay. So this was the concept of in degree. Fine. Let me take a bigger example to explain you the algorithm. If I can find one. I think this is a good one. Okay. See. So here if we find out what is the in degree of each node. So this will be 2 for this, 0 for this, 1 for this, 2 for this. Like 2 nodes are coming, 1 node is coming towards it, and 0 node is coming. So if we have to find out the sorting or the topological sort of a graph, we know that we want those nodes first which are not dependent on any other nodes. And how can we say that a particular node is not dependent on any other node? That means they're in degree 0. There is no other nodes which are coming towards them. There is no nodes to which we are dependent on. That means 5 and 4 both can be considered as the terminal nodes, or can be considered as a node which are not dependent on anyone else. Correct? So we can say for sure 5 and 4 will come before anyone else. Fine. Now what I'm saying, let's suppose I'm saying I will no longer be having this 5 with me. So if 5 is no longer there with me, that means this edge will get removed as well. So when I'm saying that this in degree node will will be removed, that means whatever was my in degree before, I can do minus to this, And if this turns out to be 0, that means we can consider this node as well to be a terminal node, or to be a node which is currently not dependent on anyone else. The only node which this 2 was dependent on was 5, and we have already picked up, or we have already removed 5. That means 2, we are sure that we can easily include 2 to our list, saying that whatever 2 was dependent on is already given to us. So if I take sequence in this way, then we can say that if I'm at 5, I can easily visit 2. So this is the right sorting of my graph. Fine. Now I'll ask that, okay, what about if I remove 4 with whatever I have? That means this edge will get removed. That means my value of in degree for this node will now be 1, but for this one it will be 0. That means I can pick this 1, but I can't pick this 0, because this 0 is still dependent on, okay, it is not dependent on 5 anymore, because when we removed 5, we have to remove all these 2 edges. That means our incoming nodes for this 0 was already 1, and when we removed this 4, the in degree further got removed to -1, and that means we can now take 0 as well. So what I'm saying, if I remove 5 and 4, those are the terminal nodes, or those nodes which are not dependent on anyone. If I remove these nodes, that means I can now consider the 0 as well. Whatever nodes that 0 was dependent on are already picked up by me. So that's what I can say, that yes, I can pick up 0. And then we will see, yes, I can pick up 1 as well. So when we pick up 1, we will remove this edge. That means this will be removed to 0 as well. To 1. And once we remove this, we will see that, yes, we can remove this edge as well, and in turn this will be 0. So you can follow up a sequence over here, that always 5 and 4 will be the first node that you will get, then 0 is the node that you can extract, then 2 is the node you can extract, then 1 is the node you can extract, and at last you can extract 3. So what does this entire sorting means? That if I write the order, it will be something like this. Okay, command Z, can I do command Z? Yeah. So if I consider this, that means it is now in a sorted position. To reach 3, we are dependent on these values. To reach 1, I am dependent on these values. To reach 4, I am dependent on these values. Basically, it is a sorted part of my array, of my graph, and that's all it is asking. So in questions like course scheduler, it might ask you that to take course B, make sure you have taken course A first, and to take course C, make sure you have taken course B first. So it might ask you that what is the sequence of course that you should have taken in such a way that you are able to take all the courses. So you can say, yes, initially you have to take A first so that you can take B, and once we take B, then we can say that now you can take C as well. So this is the course sequence that they are expecting, and this is nothing but a pure topological sort. So that's where topological sort comes in picture. Now let's understand the code first. Okay, let me remove everything. Okay, so in the code, what I'm doing, as we discussed, we will figure out the in degree for each node. And if at any node the in degree is 0, like for these 2 nodes the in degree was 0, right? So I'll pick up these 2 nodes and I'll insert them in my queue. Why I'm inserting that in my queue? So that when I apply the BFS approach, I can pick up all the elements who are neighbor of these nodes and can keep on reducing their in degree in such a way that I will no longer be considering 5 as a node. Just remove whatever edges that I had, and by removing edges I mean decrease the in degree that I had. And once I decrease the in degree, and if at any point my in degree becomes 0, that means we are no longer dependent on any other node. At that point I'll add this neighbor inside my queue as well, and this loop will go on again and again and again until my queue becomes empty, and we will then return the integer or the output that they are expecting. So if I have to dry run this very quickly, what I'll do for this question, I got to know that okay, 0 0 were the in degree for these 2 nodes, 2 was the in degree for this, 1 is the in degree for this, 2 is the in degree for this, and 1 is the in degree for this. Fine. In my Q, I ask that what all values have 0 with it. What all values of in degrees are 0 at this point. So it will say 4 and 5. Both of them are not dependent on anyone. That means I'll add 4 and 5 to my Q. So this will be 4 and the 5 will get inserted. Fine. So the good part about Q is that it is a first come first out solution, where whatever value we are inserting at the very first point will be the first value that we will be removing at the end of the day. Fine. So I entered inside my this and I asked that, okay, let's remove the first value that you have. So I removed 4 and I added 4 to my answer array. Fine. So once I removed 4, I asked that what all neighbors do 4 have. So 4 have this neighbor and this neighbor. So now I'm saying remove both these dependencies, and when we are saying remove these dependency, we means decrease the in degree. So the in degree for this will become 1 and the in degree for this will become 0. And then I'm checking if at any point any of the in degree is 0, that means I can consider this as one of the endpoints, one of the nodes which are no longer dependent on any other node. So if we remove 4, we can easily consider 1. If someone asks that you have to reach 1, the only way is to reach 4 first and then 1. There is no node in the middle or in the end or in the start. So that means I will consider, I will add 1 to my Q. That's what we are saying. Fine. In the next loop, I removed 5. Fine. I asked that what all nodes 5 is connected to, just remove both the edges to that. So this will become 0 and this will become 0 as well. So the moment these two value became 0, what we are doing, we are inserting them to our Q. That is 0 will get inserted and the node 2 will get inserted. Now with the loop, we will remove 1. We have already removed 5, we have already removed 4. This time we will remove 1. When we are saying we will remove 1, okay, what does this mean? This node will get removed. And once this get removed, that means decrease the in degree for this neighbor. So we will decrease the in degree for this. The in degree will become 0. Fine. Sorry, the in degree will become 1. But we will not add it in my Q, because the condition to add the value to a Q is that the in degree should be 0. But that is not true. Fine. So we will not do anything. And then we will go to our next node, that is 0. I'll remove 0. I will remove 0, but I can see that there is no neighbor of 0 that I can go to. So I'll not go inside this for loop and we are good. Then I'll remove 2. The moment, okay, I forgot to add these values to my sorted array. The moment I remove 2, I'll see that I can now add it to my array and remove the edge that I had, and by removing the edge, this value will become 0, and the moment it becomes 0, I'll add it inside my Q, and now the final value that will be there in my Q will be 3, and this will be the value that will get popped out now, and thus the Q will end, and we can return the sorted array. So if we see this carefully, what is happening, we are expecting that the 4 should come, 4 or 5 should be called first. Once we are on these stages, we can directly reach to 1 and 0 stage, and once we are in these places, we can directly visit 0, 2 and 3. So this is what the sorting of an array means. So you will see that you will use this structure or this part of algorithm to find a lot of problems in graph which are dependent on past values, or which need you to be on the past stage to be there in the current stage. So this was a little bit about the topological sort. Now if we talk about the space and time complexity for this, let's start up with the time complexity. We are traversing over the entire adjacency list. So we can say that the number of all the elements inside my adjacency list is nothing but all the edges that I have. All the edges that I have into 2. Does this make sense? So if I ask that what all 5 is pointing to, 5 is pointing to 0 and 5 is pointing to 2. Correct? So I'll be visiting these degrees for 0 and 2, and that means I'll visit this 0 and this 2 that is inversely proportional to how many edges I had. So we can say that the time complexity will be O of E. Okay. If we talk about the time complexity for this for loop, it will be the number of nodes that we have, the number of vertices that we have. If we talk about the Q that we are using, what this Q specify over here, we know that if we have V vertices, right? Then for these many vertices, there are some particular nodes that there are some edges that we will go. So if we are at this node, we will traverse for two edges. If we are at this one, then we will traverse for these one edge. So every time what we are doing, when we are saying I'm exploring the neighbors, I'm just exploring all the edges that I have. Correct? So the total number of time complexity that this queue will take will be the number of vertex plus the number of edges that I have. So this will be the time complexity for this queue. Overall, we can say that the time complexity that we will have will be O of V plus E. Fine. Let's talk about the space complexity. We are using, let me see if I can change the color. Okay. So if we talk about the space complexity, this is of V, we can see. This queue, let's talk about this queue. And in the worst case, what can happen? None of the edges are actually related to each other and all of them will get added to this queue individually. That means in the worst case, the time complexity for this queue can go till O of V. Fine. If we talk about this queue, that's overall this means that yes, the space that this queue will have is O of V. So, and we will be using one more space, that is to store our actual result. So overall we can say it is 3V, that is equal to O of V. So this will be the space complexity and this will be the time complexity. Hope it helped. I'll try to come up with more such algorithms rather than questions, because algorithms cover more, I would say more knowledge than just one question. So I'll try to come up with these algorithms more. It was my first time explaining an algorithm rather than a question, so it was a bit slow. I did some things were not very organized, I would say. So I'll try to come up with more such videos and I'll try to be more organized going forward. Thank you.